Now let's review this chapter dealing with quadratic equations. This first problem has an x squared isolated on the left-hand side, so I'm going to choose to square root each side. Technically, there's an absolute value around this x when I square root that, but when I remove the absolute values, that gives me a plus or minus on the right-hand side with the square root of negative 48. Since 48 breaks down into 16 times 3, I can simplify this as being x equals plus or minus 4i root 3 as our solution set. For number 2, again, I've got a quantity squared with no more x's anywhere else in the equation, so I'm going to choose to isolate this quantity squared by subtracting 8 on each side of the equation. This leaves me with x plus 5 quantity squared equals 11, and when I square root each side, I get x plus 5 equals plus or minus root 11. Subtracting 5 on each side gives me negative 5 plus or minus the square root of 11. This problem could have been solved using the quadratic formula had we distributed out that square combined like term and put it into standard form, but I think this was the quickest approach on this problem. For number 3, we're being asked to solve in two different ways, and the first way would be factoring, and I try that, but I don't have two numbers that multiply to 7 and add up to 10, so that is not a good approach. So I'm going to move on to completing the square. I will have x squared plus 10x, leave a blank, equals negative 7. There's no leading coefficient to divide through by, so I'll move straight to cutting in half. The 10 cuts in half to a 5 and squares to a 25, which I'm going to add to the right-hand side of the equation to keep that balance. Now I have x plus 5 quantity squared is equal to 18. I can then square root each side. This leaves me with x plus 5 is equal to plus or minus the square root of 18, and the square root of 18 is 3 root 2. X then is equal to negative 5 plus or minus 3 root 2. Now, as a second way of solving this problem, we can use the quadratic formula because it's already in standard form and we already can identify easily a, b, and c. Let's begin with the discriminant b squared minus 4ac. This becomes 10 squared minus 4 times 1 times 7, and that will be 100 minus 28, which is 72. Moving on to the rest of the quadratic formula, we'll have x equals negative b plus or minus the square root of 72 all over 2a. This becomes x equals negative 10 plus or minus, well, the square root of 72 is 6 root 2 because 36 times 2 is 72 and the 36 square roots to a 6 all over 2a, which is 2 times 1, which is 2. Now you've got to be very careful with how you cancel, because that 2 cannot be canceled with either the negative 10 or the 6, but rather with both of them. And we really want to factor out a 2 from the numerator to have negative 5 plus or minus 3 root 2 all over the 2, which we can then reduce to x equals negative 5 plus or minus 3 root 2, and that is consistent with what we had up above. For this next problem, I would try factoring, but I don't think with 3's and 2's I'm going to be able to create that 15. And I really don't want to factor out that 3, because if I do, I'll have a 5 and cut in half. That will be a 5 cutting in half gives me a fraction, and so I'm going to just go straight to the quadratic formula here. The discriminant b squared minus 4ac is 15 squared minus 4 times 3 times negative 2, which is 225 plus 24, which is 249. Now, I'm going to have to break that 249 down, and I do know that 3 goes into this because 2 plus 4 plus 9 is 15, and since 3 goes into 15, 3 goes into 249. But I'm going to find out that that's going to be an 83, which is a prime number, and that tells me I'm not going to be able to break the radical down. So here we go. X equals negative b plus or minus the square root of 249 all over 2a. Substituting our values in, we have negative 15 plus or minus the square root of 249 all over 2 times 3, which is 6. I could cancel the 15 and the 6, but because the 3 we'd be canceling is not a factor of the whole numerator, I'm going to leave this answer as is.